Okay, good afternoon, everyone. Welcome to the HAO Colloquium. Today, we're very glad to have our visitor, Professor Binzhen Zhang, to give a talk. And many of you know him very well, but still, let me give a brief introduction based on the short CV he sent it to me. I hope I'm not missing any highlights here. Okay, Professor Zhang got his bachelor's degree and a master's degree in electrical engineering from Zhejiang University, one of the top universities in China, in 2005 and 2007. And he then went to Dartmouth College and worked with Bill to get his PhD degree in engineering sciences. So it's really a special background of a lot of engineering exercise. And after that, he had been working as a researcher at Dartmouth from 2012 to 2016. He then spent 2 years here at the HAO as a postdoc before joining the University of Hong Kong in 2017. And he's now an associate professor in the Department of Earth Sciences. And Bin's research focuses on developing global scale numerical simulations to model planetary, solar wind, magnetosphere, ionosphere, upper atmosphere systems. And he has special expertise in numerical MHD simulations and has made fundamental contributions to the Gamera global MHD model. And today he's taking us to visit the outer solar system, Jupiter and Saturn. So let's welcome Bin.
Thanks for the nice introduction. So it's interesting that after more than 15 years, 17 years, you still cannot get rid of me. Or vice versa, right? So it's so nice to be back here. The last time I gave a talk here was 2019. It was right before COVID. It was AGU and this, and it's nice to be back and be working on something differently and thinking about more bigger pictures on what to control the morphology of planetary aurora. And what I want to do is I want a simple theory to describe all the planets. So this is what we're trying to do, right? So this gets a lot of help from my colleagues like Oliver Brembos, Peter Delamere, also Bill helped a lot, and my colleague Zhonghua, and then my postdoc JJ. Right. So planetary aurora, they're very different. It's not changing. What happened?
Just try click.
Click. Yeah. No, it's not changing.
See the pretty pictures.
It's post, right? What happened?
Getting stuck.
Ah, here we go.
Oh,
okay.
What if I just make this?
Yeah.
Can you see that? Oh,
Yeah,
it's
yeah.
just okay.
Yeah,
Let's
yeah.
do this. All right, let's do this.
The initial condition is not right.
All right. So if you look at aurora, right, people working the geospace folks are very familiar with aurora. So you see the Earth aurora, which is very easy to identify. It's a circle, right? So if you go to Alaska or Iceland and you can see these structures, then you will not believe this is a real aurora oval, but the dynamic structures are very much more dynamic. But if you look at others right now, thanks to this is the Hubble Space Telescope (HST). It's a view from figure from my colleague, and showing the aurora of Saturn. They look, so you can have some sort of like aurora oval like the Earth. So the day side is over there because this is HST. So the side you cannot see is the night side because the HST is viewing from the Earth. So you only see the day side. This is 12 o'clock local time. And then sometimes you have these polar cap of Saturn is like half filled or completely bright, right? So you can go to Jupiter, which is a completely different situation, and you have the Jupiter aurora has something like an aurora oval. So if I talk about this in the outer planetary magnetic community, I will get hammered because they want to say this is basically the main emission, and this is the polar emission, this is the equatorial emission, etc. But I'm just going to say we have aurora oval, but it's also bright in the polar.
Are those all in the same wavelength or are they different?
Yeah, these are UV ultraviolet.
So what is in the left and right Saturn here?
Two different images. So the Saturn aurora changes all the time, and Jupiter is always more or less like that, right? So the question is why they're so different.
Is that always a northern hemisphere, or you can see both?
Well, you can see the Saturn does not have a tilt, so it's more or less symmetric. But Jupiter is not. Jupiter, the southern hemisphere has a weaker field and has features like this, but not as prominent. It probably emits a different wavelength. So question is why they're so different. Or you ask the question, why would you expect them to be the same, right?
Since the best one on the Jupiter is this bright place or aurora.
Or emissions.
Other than that, the ring at
Yeah, so
in the middle of the sun.
Instead of you have a ring and you have
Yeah.
lots of emissions inside,
Oh.
right? So that's very different, very, very different. So why do you expect them to be the same? Of course, they're not the same, right? So if you look at this image, right, you have the solar wind driving the magnetospheres. So now the question starts. If you look at the planetary parameters, right? So magnetic moment is, of course, orders of magnitude different. The radius is different. Jupiter radius 11 times larger. And the spin, Jupiter spins much faster, 10 hours per spin, right? So the radial velocity is huge. And of course, the IMF conditions are different, and you have internal mass sources. The Earth is negligible in general conditions because polar wind is very light, so it's not available. So in these pictures, you can see in the classical textbook pictures, this is what you see from the terrestrial magnetosphere, Coronian magnetosphere, and the Julian magnetosphere. So if you look at these pictures, you will see the interaction is basically from the solar wind driving a dipole field with the compressed day side that stretch the night side, right? So with these magnetosphere topologies, you would not expect the auroras to be that different. They're actually completely different, right? So this is the Earth UV aurora. These are the images from Saturn. You have a night side, oval, day side emission, polar emission, and Jupiter is basically the oval plus the polar emission. So if you look at these pictures from textbooks, right, so these magnetic topologies are not enough to explain the aurora morphology. Because if the magnetospheres look like this, you would expect the aurora all look like that, right? But they're completely different. So what's going on? The answer is in the magnetosphere. And we know that the Julian magnetosphere and the Earth's magnetosphere is completely different in global morphologies, right? So this is the global simulation. This is a X-res simulation, very high resolution simulation of the Julian magnetosphere. And what you can see is that this is the equatorial plane, shows the plasma density, and that's the Io, Europa, Ganymede, and Callisto. These are the orbits. And you can see the Io because it's very volcanic, right? So you have lots of plasma coming out from the Io, forming a torus. And these plasma are transported radially outwards to the outer system and forming these kind of interchangeable structures. And then the day side, the magnetosheaths, everything is very different. And then one key thing is that if you look at the polar region, this is the current, normalize the currents. You can see the polar region of Jupiter is very relatively bright. If you look at the currents in the Earth simulation or Earth magnetosphere, it's pretty dark, right? So corresponding to a bright polar region and a dark polar region, right? The question is why the Julian system is so different. So thanks to Juno, and we have much more information. So this is, for some of you probably not familiar with Juno. So this is the original Juno orbit. So now there's a capture orbit with 53 days, going really close. Perigove goes to like 5,000 kilometers, basically the surface of Jupiter. Further out, and that's the image. That's a real-time image, not real-time image, Xera image from the Perigove 45. So this is the 45th orbit of the Juno. So something happened with the thruster. So the Juno orbits never get into this 14-day orbits. So Juno got stuck in this very long orbit, 5,000 kilometers towards the surface, almost 100 Julian radii in the tail, which sucks for gravity and other stuff, but it's great for space physics, right? All the important thing happens here, right? So this is what the Juno projects have. So with the collaboration with my colleagues who are working in the UVS teams, so we'll be able to get these aurora images, right? So this is the aurora image. That's the what happened? Okay, this is the aurora images. This is the ultraviolet UV aurora from the northern hemisphere, from Perigove 4, 5, 6, 3 consecutive orbits. Northern hemisphere, southern hemisphere. That's the emission in the ultraviolet wavelength, and this is so-called the count ratio. Count ratio indicates the energy. So you can see that instead of having an aurora oval, you have lots of polar emissions, and in terms of the polar emission is even more energetic. And so this one goes to hundreds of keV, even to keV to megaeV, and to even hundreds of megaeV for very high energy here. So the southern hemisphere is slightly different. You have the aurora over, but you still have some times because the magnetic fields are different. So the precipitation is not expected to be the same. The northern and southern are very asymmetric. So, but in general, you get this. So if you look at the precipitation or the emission from the northern hemisphere, these in perigel 16, 17, and 18, they all have these kind of features here with an oval and a filled polar cap in a dark region, right? So this gives some ideas like why the Jovian magnetosphere, the aurora is so different. And we did some study to figure out the differences. And this is basically from our simulation 3 years ago. And looking at the magnetic topology of the Jupiter's magnetosphere. And you look at this, it's not linear. It's not a typical like open polar cap region. So what happens here is that pay attention to the black field lines. So the black field lines are coming out from 85 degrees in the magnetic latitude. And you see that these 85 degrees all the way to the pole, they don't close to the solar wind. They're coming out from the northern hemisphere and going back to the southern hemisphere. So suggesting that the Jovian magnetosphere is largely closed, right? So when we first got this picture, I saw this, I did not believe this because I started with the Earth background, right? Never seen things like this. And it's really easy to make mistakes in a simulation. You treat the wrong parameter, you get the wrong simulation easily, right? But my colleagues kind of convened, they showed me with the observations and things, and they're trying to say that eventually we figured that this is physical rather than numerical. So if you look at the
what's the blue line?
Oh, the blue line is near the pole, but they're really open to the distance, very long to all the way to the end. And the reason they're connecting the back because my simulation ends somewhere here, so they are numerically connected. So they're largely box, they go all the way to the back. So the blue line is called distant open.
It's a thin region where it's open.
Yeah, it's a very dynamic region, but it's open. But
It's small, right, in terms of area.
Yeah, small, but it probably doesn't matter because beyond a few hundred RG, it's super atomic again. So information cannot come back. So you probably cannot see anything in the ionosphere because this is so distant.
Are the green lines, the open framework connector?
Yeah. Green lines to the IMF. The IMF is that Jupiter is nicely BY because it's a proper spiral. So there's no busy challenge. Not at all. Not busy. If you talk to a friend who's no busy. Right. So it's all BY, trying to make her happy. All right. So this is the topology of the Julia simulation that we did from the XZ plane, which is the meridianal plane. And this is viewing from the equatorial plane. You can see the close the field and then the close the polar region and then connect to the IMF. This is viewing from the sun. Right, so the polar field lines coming out from the northern hemisphere, going back to the southern hemisphere, right, which is very bizarre. And these one connect to the. So with this one, and we have more and more evidence showing that this topology is possibly correct. One of the direct measurements is that the Juno did the orbit, flying through the pole and going back to somewhere 100 RJ, and they show exactly the same ion population and dispersion. So which means that these two regions are remotely connected near the pole, right? So that's the difference. And also other evidence, for example, this is also a nice paper. Oops, just came out. This one paper just online a few weeks ago, looking at the ionosphere cusp. Because if you look at simulations, and this is a nice diagram from my postdoc JJ, and showing this is viewing from the sun. Jupiter's here, but Jupiter is actually smaller. So if you look at this, and you will notice that the cusp region, which is the direct entry of the solar wind to the inner region, is actually in the dawn-dusk cut. Instead of at the noon, it's actually dawn-dusk region, right? So they did this survey with the Juno data, and they found the cusp region, which is about somewhere in 15 o'clock, and they have a survey and showing that the cusp is basically on that region. So this is also an evidence showing that the topology is probably correct. And so I'm not going into the details. Yes.
You said it's cusp in the dusk or dawn dusk.
Yeah.
That's because BY or the
Because of the rotation.
rotation.
Yeah. because the inner region rotates much faster and the outer region rotates slow. So you can imagine that any reconnection happens on the day side,
Mhm.
the flux tubes rotates to
Okay.
the other side.
Okay.
So the cusp basically disappears. This also answered my question because I remember that John Line gave a simulation about the Saturn magnetosphere maybe 12 years ago at Dartmouth. I asked him the question, where is the cusp? Because he was showing the noon midnight XZ plane, there's no cusp. You have to look at the YZ plane and to see it. Right. So the reason why the topology is so different is because of rotation. So if you look at the reconnection separations, this is a comparison between Jupiter and Earth. So these are the field lines and the red curve. Pay attention to the red curve. That's the separatrix, reconnection X line separatrix on average. So you can see that the Jovian separatrix is very hemispheric asymmetric. One on the dusk side and moving to the polar region because of the rotating lobe. So you imagine the IMF is this direction. So the reconnection happens mostly along the high latitude. While the Earth is basically a typical, it's a model that you expect from the component to the connection somewhere with the IMF BY condition imposed. So the question is why the Jupiter reconnection or the topology looks completely different. So a couple of ideas is that if you look at the base side of the reconnection, which is the reconnection driving the anti-sunward motion of the flux tubes, and that reconnection potential at the Jupiter is about 400 kilovolts. But then if you look at the rotation potential, which is also a co-rotation potential, let's call it that way, the co-rotation potential to the equator is much larger than 20K. So, which means that the reconnection potential is negligible in the Jovian magnetosphere compared to the co-rotation. So it's a rotationally dominant magnetosphere, which with Earth, it's a completely different picture. It's mostly driven by the solar wind. While the Jovian is driven by the rotation. Now, this is when we start to realize that the two magnetospheres are fundamentally different. So now, question. Is there a way to describe the planetary aurora morphology to the first order? For example, I use a planet X to describe all these aurora morphologies. It sounds ridiculous, right? How would you think about things like that? Well, the reason is because the Jovian simulation is extremely expensive. So the simulations I showed you, we did this in one of the supercomputers in China. It cost us 10 million core hours for one simulation. Maybe nothing compared to Raycom X, but still, we are a smaller community.
Comparable.
10 million core hours for one simulation, that's quite expensive, right? So the original motivation, because I'm a very cheap person, right? So I want to do a cheap simulation to represent all these cases. Like, what can we do with that, right? So now the idea comes from the modes of magnetospheric circulations, right? So there are two modes of magnetospheric circulation. The first one is the solar wind-driven case, which is known as the Donji cycle. Although we know the Donji cycle does not explain most of the things that we're studying, but it gives you a general picture. So what happens in the Donji cycle is that the interplanetary stuff, magnetic field, comes with the solar wind. So you start to have a day-side reconnection, open the magnetic field, convect through all the polar cap and have a night-side reconnection, close it, right? So this is completely driven by the motion of the solar wind. So it's driven by the intensity of the IMF and the velocity by the solar wind, right? So you can see this picture is called Donji cycle, it's solar wind driven. And there's another mode, and most of you here are probably not very familiar with, it's called the rotation driven cycle, which is called the Vesalius cycle. So the original plot from Vesalius is incorrect. So I'm using Peter Delamere's plot, which I think is a better representative, but it was originally developed by Vesalius. So what happens here is that you're looking down, this is looking down the pole, and you have the plasma or the magnetosphere rotating around. So inside a given distance, it's a rigid co-rotation of the plasma, so plasma co-rotating. Outside this region, the plasma start to deviate from the rigid rotation, and then you start to have dynamics and stretch of the tails. So reconnection, magnetic reconnection happens somewhere on the dusk side and somewhere downside. Like this is due to the stretch of the flux, dipole flux tube, like the differential rotation in the sun to generating all these. So it's like a dynamo process. So this process is entirely driven by the rotation, right? So this is called the Vesalinis cycle. Although there are still some questions, but the key idea is that one is solar wind driven, one is rotation driven. So how do we quantify these two terms, right? So think about these looking at the topology aurora of planetary magnetosphere. So we first think about this with these factors, right? Upstream conditions, of course, every planet that's different, that's directly related to the solar wind intensity. Periods of the rotation, of course, that's related to how strong the rotational drive is. Radius of the planet is important because that defines the size of the magnetosphere. That's the relative time scale of the solar wind versus rotation. And also the planetary field. Right? So these are the first order factors. And also there are other high order factors, internal mass, moon, polar wind, outflow, conductance. That's our Bill's favorite, and they're all ignored, which is great, right? So he doesn't have questions. Right, so I think these are second order effects. Why we think these are second order effects? Because we did test simulations by incorporating internal mass, different conductance, and outflow, and to show that the global morphology is not significant, it's not changed compared to the first order ones, and also other atmospheric questions.
Is it because the solar winds are much weaker in those places, and relatively speaking, your rotating speed is much faster?
Yeah.
That changes the dominance of which ones?
Yes, yeah, that's my next slide. And there are always high order effects, right? Because you may have alien impact. Because I work in a department that people work in astrobiology. So besides geology, astrobiology is also important, right? So we will include the alien stuff later. Right, so a couple of thoughts. So doing individual planetary magnetosphere simulations are very expensive, like the Julian simulation is extremely expensive. And you have too many knobs to turn, right? Everything's different. And trying to compare the Earth with Jupiter is not fair. You not compare apples to apples, right? You not just compare apples to orange, you compare apples to right? So that's a completely different thing, right? So the second one is, can we use one magnetosphere as a baseline to evolve to other systems, right? So this is the idea. And so the idea is that we do numerical experiments to evolve the Earth to Jupiter, right? So this is what we think about, right? So we only consider first order effects. So quantitatively, so we consider two effects. One is the solar wind. So the solar wind effect is we consider the effects of merging. So by looking at the phi reconnection, which is the reconnection potential. So it's very nicely, Jeremy Ulla has this semi-empirical equation to describe the reconnection potential as a function of upstream conditions and the magnetopole size of the magnetos's poles. Basically, it's a solar wind intensity integrated along the size of the magnetosphere. So if the magnetosphere is larger, then you have a larger solar wind impact in this way. And the other one is the rotation potential. So this one is simpler. So what we do here is we just look at the mapping point in the dipole map, which is not that accurate, but close. So mapping point of the co-rotation potential. So if the system rotates, you have an electric field in the latitude and the direction. So E cross B gives you the rotation, right? So this is the potential drop to the pole to the location where the magnetopole is. So that potential describes how fast the magnetosphere rotates. And this potential describes how fast the solar wind merge happens. So let's do a simple divide, right? Because we're trying to do subtract, it didn't work well. So let's do a divide. Let's compare these two terms and we get this parameter. And I hope this equation is correct. Can you check it? Okay. Yes, that's correct. So this is the parameter that we're looking at. I call it R5 parameter, looking at the competition between the solar wind merging and the rotation of the planet itself. And it's relatively complicated, but some idea you can see that the ratio is proportionate to the IMF. So if the interplanetary field is stronger, of course, the solar wind influence is larger. And also, if the rotation velocity is faster, right? If you have very fast spin magnetosphere, of course, this is dominated by the denominator. And also, it's interesting that the intrinsic equatorial field dependence is only to the power of 3 to 2. It's not linear, or -1. So there's a reason for this. And another surprising conclusion is that the dependence on the solar wind velocity and solar wind density is different. Right? So if you increase the solar wind velocity, the solar wind control increases, right? If this term is a larger, which means there's more solar wind control, smaller, more rotational control. But if you increase the density of the solar, you have very dense solar, it goes into more rotational control or less solar wind control. And this has something to do with the size of the magnets. We're not going into the details.
A quick question here.
Yeah.
So are you aware of any correlation between the solar wind speed and density itself?
No, we don't. They're constants. So I'm not looking at the change. They all combined in one parameter.
Okay.
So whether they're linked or not, it's not a problem with this picture, right? So with these ideas, so you would expect that a bigger planet will be more rotational control, right? Think about this. If you have a planet which is the size as half of the heliosphere, that's going to be all rotation, right? The solar wind is not going to do anything. A stronger magnetized planet may be more rotational control if you have a very large magnetosphere and the solar wind takes a very long time to travel. It's going to be more rotational control. And the velocity and the magnetic field may have different roles in controlling the system, but that's a more high order effect. Right? So based on this equation, now this kind of explains the reason why we want to do this is because you can see that for each planet, everything's different. IMF's different, rotation's different, B field different, everything's different. So, but looking at the R5 parameter, it's a one single parameter, right? So let's think about numeric experiments like this. So this is the list that I did looking at all these parameters at the Earth, but I'm using relatively smaller IMF, 2 nanotesla rather than 5, because if I use 5, I need to spin up even faster. Right? So I use 2 as a baseline. So if I do these parameters from the Earth orbit, and you can get in, the ratio is about 10, which means that the reconnection potential is 10 times larger than the rotation. Right? So that kind of describes the Earth's situation. Right? So it's mostly driven by the solar wind. And if you look at Jupiter and Saturn, it's covered by that one. So if you put the parameters as Saturn and Jupiter, Saturn is about 0.38. So it means that, yeah, okay, great. 0.38 means that these two terms are comparable, or the rotation potential is slightly larger and also varies. And the Jupiter is less than 0.1, which means that Jupiter's co-rotation potential is much larger than the reconnection potential. So these parameters, so for each planet, we have all the simulation, but these guys are very expensive because it takes hundreds of hours to kind of settle down. So the idea is that let's spin up the Earth. So if we spin up the Earth, and you can basically control this parameter to be 0.4, 0.5, 0.2, and 0.1. So by spin up the Earth by 20%, 20 times faster, 50 times faster, 100 times faster, just by changing the spin rates of the Earth, right? And then the idea is that we just run a cheap Earth simulation with these parameters comparable to Saturn and Jupiter to see if we can reproduce these aurora morphologies. Yes.
So what essentially determines the commutation cost? So sounds like the rotation speed is not, but just the size of the.
It's the size, yeah. Because the Jovian Ionosphere, if you want to simulate, you need to have a box almost like 1/10 of the heliosphere. It's a gigantic simulation box. It's basically the size, right? All right. So the first time I showed this in the geology department, I immediately got criticized by solid Earth geologists because they say that if you spin Earth that fast, it will explode. There's not enough gravity to keep it open. So to get around with that, we call these a super Earth. Right, so they can be extremely dense. So that's a floating in space. We're not spinning up.
Another universe.
So that's why they call it super rotating Earth, right? So the density is much higher than Earth, so they don't explode. Right? Right. That's just right. So to do this, what I use here is that I start with something really simple. So we start with the vanilla magnetosphere model, just with the Gamera solver. heritage from the LFM code. So we use a dipole field. We use constant upstream conditions to fix all the parameters, and we don't have conductance gradient. And no tilt, no tight GCM, no RCM, no everything, which is great. And so you can't ask me any questions about it. But this no moon mass loading, that gave me some trouble when during the talking to the outer planetary people, because that's important. So we just take the MHD solver with the electrostatic ionized coupling with constant conductance to see how the system respond to the faster rotating Earth. Right. So to get this done, and we found that the quality of the numerical solver is very important. So the high resolving solver is very important. So this is a test simulation showing you the direction of the structure moving around one cycle, and you should go back to the original space. But you can see that if you don't have a good solver, right? This is the first order solver. This is the central solver. This is the Van Leer TVD solver. CIP, we know, and this is the one, the seventh order solver we're using. You can see that other solutions doesn't do very well. Give you all these artifacts. So these gray areas are less than the negative density. Give you all these either smeared out or less smeared out, but compared to that solution. So the accuracy of the solver matters a lot. So we've also done numerical simulations using a solver like this. And regardless of how fast you spin the system, it all looks like the Earth because it's so diffusive and then you just can't handle the propagation of the waves. So we've also done simulations. I like doing all kinds of crazy test simulation to try to break the solver. So this is a trace simulation from, actually it's originally developed by NCAR, the atmospheric people trying to look at the variation of these, the direction of these structures in a time changing horizontal wind system. And you can see that the solver is relatively doing a good job, but this is a very tough, this is about the best that we can do. So we can talk about this later. And also the OZCOM problem, we've been looking at this all the time. So this is our Cartesian box solving the OZCOM vortex, evolving from the uniform to smooth to shock and all these, and the reconnection is showing this forming of magnetic islands. This is Cartesian grid. This is non-orthogonal Cartesian grid. So you would see that by looking at this, you can see that the Cartesian grid is doing a pretty good job compared to the others. So there's no analytical solution for this one. So people just compare their high resolution simulations. So the distorted Cartesian looks decent in most ways, but you still see some asymmetries and things. And that's because although there are reconnection happening here. So when reconnection happens and then the grid size slightly off, you change the symmetry because this simulation requires, the symmetry requires a very high level of symmetry in the truncation error. So the truncation error is slightly different. You see this. So this is also a question I got. I gave a talk a while ago trying to show that we have a solver that can resolve solve the MHD equations, which is grid. That's not depending on the grid. But I also get this question like, given that your Cartesian solution looks pretty good, why bother going to that one? Why bother using complicated non-uniform grid instead of using Cartesian grid? I think it's a good point. I don't have an answer for that one. So the Cartesian solution looks pretty good. All right. So the development is fun. So we spend a lot of time looking at this, and we still have more development coming. So this is basically I worked with Hong Yang on this gas kinetic double adiabatic energy solver. You can see that the alpha waves, the waves travel at a different speed when you have a different anisotropy, right? Different ones. And then this is the theoretical speed, that's the numerical speed. He's done a very detailed description of this solver, and then it's published in GCP. And recently we're also working on solving the MHD equation in the cylindrical and spherical geometries by solving different equations. So these are the orthogonal solvers. So everything has to be changed because now you're solving different equations in the system. So you can see that these are test simulations. And one thing he really did a good job is the ring average stuff that was surprising. So here is the advecting of the field loop into a pole and going through, and you almost don't notice any artifacts, which if you look at the non-orthogonal solver and you have these small changes when you're going across the pole and somewhere, and maybe a little. So this is the one is because that we haven't changed the reconstruction when you're going across the closer to the pole and to make it more accurate. So these are developments undergoing, and we're thinking about doing this because the reason why I think about this is because the rotation is so important in Jupiter. So if we don't have accuracy like this to conserve angular momentum or something, then we're in trouble. So these are the developments. All right.
But you already did the simulation in stretch grid curvilinear geometry, so are you in trouble or?
No, I just don't mention it. All right, so now let's go back to the super Earth rotation experiments, right? So a couple of things I'm gonna do. Every simulation is based on the Earth. It's very cheap. It takes about 10 hours simulation hours to get everything done. Doesn't need to go to extremely high resolution. A quarter resolution is good enough. And I spin up the Earth by rotation by a factor of 20, 50, 100, and you get different potential ratios to be 0.5, 0.2, and 0.1. And then we're trying to see if we can, what happens to the polar cap and everything, right? So now these are the results, and you look at the open flux. So this is pretty complicated. So let's look at the panel in the middle. Here is that this is the ionosphere looking down the northern pole, because there's no dipole tilt, so northern and southern, they're symmetric. So the grid area, shaded area is the open flux region. So that's the polar cap open, and that's closed region. And then the field lines are foot points of these field lines. The red are at 76 degrees. And the green ones are on the boundary, which is probably basically connect to the sun. These are open field lines. And the black one is at 85 degrees. So you can see that in the terrestrial picture, which is the baseline. This is what you would expect from a Donkey cycle and Ionosphere. Very linear in the lobe and connect to the IMF and the open and also closed field lines. So once we start to spin up, right, for a factor of, this is 20 times faster, and you kind of see that the open closed boundaries start to have this weird shape because it rotates around and have finger comes in like this. And actually you see these kind of structures in the Saturn's aurora observation from Cassini. So this is somewhat close to Saturn. And in the magnetosphere picture, what you see that instead of have a linear lobe going all the way to the tail, you start to have a rotation, right? You start to have a rotation. What happens is you transport the lobe fields from the dusk side to the dawn side, because you're not changing the reconnection rates here. So there's not fast enough reconnection to remove all these rotated fields. So you start to have a little pile up here. And this pile up corresponds to some of the structures down here. And as you increase to 50 and 100, and then the polar cap becomes really this kind of swirl shaped region, like this little band region. And then there's more pile up because you transport more flux faster to the dawn side. And they cannot get reconnected, and they can have this pile up in the downside region. So this is saying that reconnection, because the reconnection rate is more or less fixed. And I checked the simulation, the reconnection potential does not change much in these. So there's not fast enough reconnection on the downside flank, and then you start to have this pile up region down there. Yes.
So I saw that the second case, the RP is 0.5, and you make that as comparable.
Yeah.
Do you have really, have you simulated the real cross point where it's equal to 1? I mean, both are equally important.
Yeah, there's one that covered about 5 times faster.
Okay.
And they're about 1, and this just gets less skewed. So it just gets less. You look at this structure evolves in.
Okay.
So it's basically more and more skewed. The polar cap is more and more skewed. Eventually it evolves to something like that. So the open region becomes basically a crescent shaped region, like it becomes a ring instead of a pancake. I know you radiation don't like pancake distribution, so this is a ring distribution.
We like rings too.
Yeah, we like rings too. So my goal is achieved, right? Because this looks so much the same as the Jupiter simulation we did. That's 10 million core hours.
Around the shaded area in the plot, it looks like it become narrower.
Become narrow, yeah. Because you're moving faster and faster and faster. So the open field region expands slightly. So the latitude expands slightly. So it becomes open flux gets less, slightly less and less this way because it rotates so fast. Before it can reconnect, it just move around, move away in this way, right? So yes,
You get episodically get eruptions like this. The notation is like building up a twisted field.
oh yeah,
It's like a CME. I mean, it's
oh yeah,
it's a closed field, twisted up, twisted up. Do you monitor the magnetic energy? Is there like sudden drop?
oh yeah, lots of them.
You have that kind of
Yeah, this is
open, suddenly
basically
open.
it's like a mini sun. I probably wouldn't call it CME, right? JM,
something like
Julian mass ejection. Yeah. So we have lots of periodicities. Lots of, yeah, because you build up, you do the stretch, build up, and then release. And this is also observed by Galileo. But we still have, I concerns about what the periodicity it is because I don't have mass load. Because the Julian plasma mostly from the Ionosphere torus, which is not included.
Yeah.
So this is not close to it. But you can see that with 1,000 times less computational resource, we basically reproduce that one.
Yeah, actually, a relevant question. So as the field line got twisted and twisted, you should expect some reconnection in the distant area, right?
It's extremely complicated. Yeah, I can show you the movies. So you have a stretch, like you have a reconnection here, and you have a reconnection X line down there.
Yeah.
And you have also the rest of the cycle extend out to the dusk side. So it's everywhere. And Peter Delamere calls it the drizzle reconnection. It's the grids is not fine enough to resolve that in these simulations.
Well, on Earth, it's called patchy or
Patchy? Okay.
intermittent
Okay.
drizzle.
Drizzle. He calls it
Like
drizzle.
rain.
And you don't consider any atmosphere at all, right? Because the balance will indeed explode.
No TAE.
I should have put on one bullet, no welcome X.
Not even that. Maybe no gravity. You don't you don't consider
We
enough
have
gravity.
gravity,
You-
but
you do.
the Julian centric gravity centric what Julian centric synchronous is about 2 RJ. It's very close. So the gravity is really negligible in most of the regions that we're looking at. For the Earth, it's super Earth, so yeah.
So their geostationary satellites are at 2 RJ.
Yeah, very close.
Boy, the radiation belts are a killer there.
Oh yeah, yes. Yeah, that's why the Kuiper orbit is very like elliptical. Right. So just speed up. So we look at we got the topology, we got simulation, we look at the auroras, right? So what I'm looking at is the Alphinic oval. So this is one review paper from Heiling's concept, looking at the Alphinic pointing fluctuating on the Earth, generating this oval. So the Alphinic oval is important because it's related to the precipitation, outflow, and the thermosphere mass density, although they're not exactly the same thing, but the Alphinic oval is kind of driver of lots of things. Unfortunately, this is recently trying to, propagating in the community is that the Alphinic oval may be also dominant at Jupiter. So this is observation from Juno with the precipitation observations. Just focus on this plot, maybe this one. You can see that the orange one is the broadband precipitation, and the green one is the mono-energetic precipitation. So these are statistics of all the Juno flybys across the oval to look at the comparison between the two. At the Earth, the broadband precipitation is about 15% contribution to the total power, but at Jupiter, it's about 93%. So which means that the Julian aurora is largely wave aurora.
How did they identify mono in the
From the spectrum.
also spectrum?
Yeah.
But
Data has got a spectrum. So you can look at it, it's a broadband spectrum.
what about diffuse? I remember people talk about a lot of wisdom mode waves in the
Personal.
okay.
Yeah.
It really is, but it's negligible compared
It's
to
much,
this.
yeah, it's much small.
Yeah.
So it's mostly waves, right? So what we look at is that we look at Alpine waves in the simulation. So we've done this a while ago. This is from Zi's paper looking at the Alphinic oval from the Earth simulation. It does a really good job. compared to the statistical observations. So you can see that the simulation can reproduce more or less these features. And she also identified this beautiful concept of alpine conduct, that where you see these structures in the low altitude because the conductance gradient is much less. That's a very nice paper. So we kind of use the same thing, which is nice because we already developed this technique to look at the alphinic power, and we don't need to do any modifications. We just look at the alphinic power from all these simulations. And here is the result, right? So look at this is the R5 value from the Earth baseline simulation, spin up 100 times faster. And you saw that these vertical lines are the nominal parameter at Jupiter and nominal parameter at Saturn. And then kind of see that the alphinic oval kind of rotates around, and to some extent, sometimes in this case, it's mostly on the dusk side. The dawn side, this is noon, and it looks like what the Cassini observation shows. And they have more power on the day side. And then this 100 times, and this oval looks like the Julian aurora oval.
Can you explain a little better what you're doing here? I mean, how are you going from rotation, or not rotation, but
So going,
R5 to
R5 decreases, that's increasing the rotation speed.
Sure.
So it's increasing the rotation impact.
What is this curve that is changing?
Which curve? Oh, that's the open percentage open. So how much the polar cap is open? For example, the Earth is almost 100% open, above 80 degrees.
And why does that correspond to alphinic oval?
Because you have those dark regions. Those dark regions are connected to the solar wind. So there's not much wave generated here. It's like the boundary, like you don't have much in the region. So this open region just gives you a sense of where that dark aurora region is, because that's also a observation in the Julian US UV image. So the conclusion is that when you increase the rotation, the polar caps start to become skewed, and then the size, the percentage of open of polar cap decreases, and eventually to 100 times faster, the polar cap looks like what Jupiter is.
The green curve is the OCD.
Yeah, open close boundary. It's the open close boundary. So this is what we did using a series of very cheap simulation to do that. So I also compared to the simulation. So this is the parameter. So I look at the Jupiter. So this is a global Jupiter simulation, expensive one. So look at the alphinic power and the distribution. And this is the super Earth with 100 times rotation. And you can see that the alphinic oval resembles what you see in the real Julian simulation. But this guy is 1,000 times cheaper. 100 times cheaper, let's put it that way. Right. So that's a good job to do.
So again, you're measuring delta E and delta B in the magnetosphere to get the alphinic power in both cases.
Yeah, it's basically the same as Kyling's algorithm.
Yeah.
I know Bill's not happy with that algorithm, but that's all we have for now. So the other ones we look at, the Saturn simulation one is about 0.5. This is the Saturn's 0.4. This is 0.5, and you can kind of see that the aurora oval have the main features on different sides, and there's more on the 185th degree, and this is related to the size of the magnetosphere, and this is a real Saturn simulation. There's something not included here, so you only get one branch of the oval due to the shift, due to the rotation, but the other side is more coming from something else that's not included in the simulation. So kind of identified. So the other one is that we got to also considering that we were looking at this equation, we only changed the omega, right? So people will ask, what if you change B or change other things, and then would the results still be solid, right? Because omega, you could get a lucky case that just represented everything. So now we did these simulations, and that's from referee. Right? So we did this. That's a very good question, because I want to know if that equation works or not, because it's such a simple equation. So what we did here is that we kept the ratio to be the same, or 0.1, like the Jupiter case. And we use a weaker B field but faster spinning to keep this term the same. And then this is the baseline. This is a slower spinning but stronger B field. Right. So the reason I didn't increase the B field a lot is that if I keep increasing, my box needs to be changed, right? Because the Bioshock will be pushed further out. So I stopped at this one. But this is good enough to tell the results is that you can see that with different combinations of rotation and B field, you can see the structure of the aurora oval is more or less the same. You have some oval-like structure. The open-closed boundary is very close to each other, although the size is different because the size of the magnetosphere is different. You have a different B field. And the emission or the alphinic power has this oval and also has some polar emission and has this dark region, right? More or less dark region down here that's observed in the Julian aurora images. If you still remember that have this dark region, they call this the collar. So that's the region. So this is a further confirmation saying that our simple theory actually works to some extent, right? So wrap up, the idea is that now you keep looking at these observations from image, HST, Juno, and with that description, now we don't think that the auroras have that much difference. It's just a combination of all these parameters. And going back to your question is that at Jupiter, in terms are extremely large. So the solar wind does not matter much. It's just the rotation that matters. And the rotation regulates all the. Look at the polar region, the dark region, that's very similar to the simulation. And we have the first, that was the first physical explanation for this region. So very cheap simulation to represent everybody.
Benjamin, there's another feature on the Jupiter side is that there's a very sharp edge, a double edge.
Which one?
Sorry,
The point side.
like here.
Oh yeah.
This kind of structure. Is there a
So this one is called the main emission.
What?
Main emission. They call it main emission. So this one maps to the region where the system started from changing from rigid rotation to sub-co-rotation.
Yeah.
So, you have rigid co-rotation inside, but further out, the system cannot keep the rigid rotation because it's too gigantic. So this region maps to where you have started changing from the rigid rotation to non-rigid rotation. So this is a very sharp in the region, but exactly cost of that is very controversial because the current theory contradicts the observations. So we are in lots of debates or fightings about what's driving that. And the other one is probably related to the further in to the torus, and these are probably related. I would say these are probably more related to the diffuse aurora you're talking about. So because these maps to further into the in between the moons, maybe inside the 10 or something. And they change, all the time. It's not every image looks different. So you just happen to have these two banded structures. All right, so they're not that different. Okay, it's about time. So the take-home message, what I learned from Earth is that the Earth magnetosphere is nice and easy to understand, right? So we know where these few lines go to some extent. And then if you ask me to draw a picture of Jupiter, we don't really know where those few lines go. I just know they go somewhere, right? And they don't agree with the classic picture of those magnetic topologies that you see in textbooks. So the Julian, picture is we're starting to changing the view of what the Julian magnetosphere looks like. So to summarize, these are some quick summaries. So the terrestrial magnetosphere has an open polar cap. That's we always know that when driven by the south polar map. When increasing the rotation of the terrestrial magnetosphere, the polar cap becomes less open, right? So the first order controlling factor from these numerical experiments is the competition between the solar wind emerging and the planetary rotation. So in the Earth case, the ratio of the potential to convection dominate because the potential ratio is much greater than 1. And Julian is rotation dominant because it's much less than 1. Saturn is very interesting, it's in between. So Saturn's ratio can go either beyond 1 or less than 1, depending on the upstream conditions. So that's why in the Cassini observations, Saturn aurora changes all the time. There's no fixed pattern of Saturn's aurora. So that's our explanation for the Saturn. And other factors may be also very important. For example, the Eoplasma torus, that's a completely different thing because the Jovian magnetosphere plasma is mostly from the volcanoes instead of the Earth that's from the ionosphere plus the solar wind. The Jovian is mostly from the volcanoes. So, but I can tell you that we also did test simulations by adding a little mass loading in the Earth simulations, and the results didn't change. So it may be in fact when the magnetosphere is very large, but with small ones, it's probably less influential. And when the spin is faster, the terrestrial magnetosphere evolves to the Jovian-like, right? And to close the talk, I use the famous talk, or not very famous quote, but my favorite quote from John Lang. Every failed simulation is an exoplanet. All right, thank you very much. Yeah, you can see Jupiter. Yeah, and also universities down there.
That building is actually the university?
No, it's behind.
Behind the building.
Okay, Mary, please.
Well, just, so again, I'm used to thinking that mass loading is what the Jovian magnetosphere is all about, because it distorts it into this, plasma disk and so forth. And yet you've obtained all of these results sort of evolving an Earth magnetosphere to a Jovian one just based on spinning up the magnetic topology, and the mass doesn't matter.
No, so the topology is more controlled by in the case of that you have the merging changes the polar region, and the rotation gives you the Vesalius cycle. So the mass, what mass does is it inflates the magnetosphere slightly and make it more energetic. So what we did in this test simulation by adding a moon course in that during the evolving, we see that the wave power is much stronger when you have mass loaded.
Yeah.
Because the flux tubes have more kinetic energy that way. So you
get more alphanic aurora.
Yeah. And then the oval actually expands because the disk, the plasma disk actually it's stretched out.
Mm-hmm.
So but it does not change those power up because that's determined by the reconnection potential and the rotation.
Mm-hmm.
So this is my argument.
Yeah, cool.
Okay.
I have a
suggestion for another, it's going in the wrong direction. The other simulation, it's even bigger than Jupiter, the sun. The interstellar wind, and so you could do it and see. I mean, obviously, it's not going to have aurora, but if there were the possibility of seeing it, you could.
Well, I think your suggestion, I will divert your suggestions to.
Well, but this is more of a heliospheric than a corona or solar simulation per se.
Yeah.
Anyway.
The project for another student.
Well, I just want to add to that. Sorry, Long, to hold you for one second. A recent paper, Nature Astronomy as well, detection of long-lasting aurora-like radio emission above a sunspot. So they do find something similar to like aurora signature in the surface of the sun. But sorry, following that one, sounds like a solar system is not enough to demonstrate how Gamera is. So are you aware of any like exoplanets that could go a totally different range of that parameter?
No, to the first order, I think this is what it is. We've done. I'm going to show you 5 test simulations, but we've actually done more than 100. So it seems to be described by this parameter nicely for all in the assumption of what happens. But others, like you have a different atmosphere, or different mass loading and things, things may be different.
Different solar wind velocity, because other stars have much stronger solar winds.
And on one case is that if the system goes to subalphinic, then it's going to be different as well. The subalphinic, you don't couple that way. The coupling is different.
Okay, we have one question from Longzhi online. Longzhi, please unmute yourself.
Yeah, so Benjamin, thank you for the very nice talk. Just a follow-up comments on what Don just said. I think for exoplanet, a very interesting idea is that for a lot of your parameters of the planets, you can translate them to with regard to the whole star and the distance to the whole star for exoplanets. So you can actually make them just a sort of a parameter of the host star itself and the distance to its host star. And then a follow-up question is, I noticed although Earth and Jupiter is very vastly different, but they are still of dipole geometry. So I'm wondering if these conclusions you have would be affected by whether or not the planet magnetosphere is dipole, or like if the tilt of the magnetic field is going to affect how these conclusions work.
Yeah, so that's a good question. So for quadruple magnetospheres, I don't know, because they're completely different beasts. But with tilt, we actually worked on a version of the equation to include the effect of tilt. It's basically a shift of the reconnection and everything. So it's just like applying a multiplier to the parameters that we're using. So, but unfortunately, we don't have observations from Uranus or Neptune in the next 20 years. So we can do whatever you want. And
Okay, thank you for that.
A quick question on the simulation side, that you used a constant, global constant conductance, like all over the globe, even for the Earth simulations.
yeah, it's in the polar region. So it's basically the 45 degrees and up. It's a constant conductance.
Okay, I mean, I would guess that if the Earth rotates so fast, then we don't have day-night difference, and all the globe is sunlit. Then we have very
Super Earth, not a real Earth.
super Earth. Okay, I mean, then we will have pretty much very high conductance all over the
All
globe.
over the globe, constant conductance.
Would that be the case in Jupiter or Saturn? Somewhere else?
Jupiter, I don't really know. There's very little observations from the Julian ionosphere. So people have some assumptions about their conductance values, but I have doubts. I have lots of arguments with people like Nisha, that's like MIT coupling with the conductance. I have a lot of problem with the conductance she uses. So maybe that's an experiment for trying to see.
Okay, we have one more item.
I mean, not TIGCM, Julian GCM.
But there was a version called JGCM, right? JTTG. Jupiter. Somebody did it a long time ago. Don't remember.
Hi, Joe. Jay. Hi, Jensen.
Okay, we have one question from online. Neela, please unmute yourself.
Yeah, thank you so much for the talk. It was very interesting. I wanted to ask you about, so we know that between the auroras and magnetosphere, there's like this region called auroral acceleration region that connects them. So, like, I don't know if Jupiter also has that, and I basically wanted to know if like there would be a difference between auroral acceleration region of the Earth and the Jupiter, and can we like somehow simulate that?
Well, yeah, you're right. So the acceleration, so Jupiter, so this is the observation from the precipitating electron spectrum. So these are very close to the surface, which means they're below the accelerated electrons. So you can see that most of them are broadband electrons. They're wave accelerated. And their energy goes all the way up to hundreds of keV. And how do they get accelerated up to that high energy? We don't know yet. So this is one. And then of course the quasi-static potential drop acceleration, or the quasi-static acceleration is the green one. That's very few events showing this one. And it looks like, to me, it looks like everything is wave accelerated. And so what the details of these are, you have to go to the kinetic regime. So you talk to like Peter Damiano's been doing some very good work on studying the acceleration of these. So so we don't have the capability of modeling that in this code. So this code will just give the energy input from the magnetosphere, say this is the energy going into the aurora. And if you compare with our simulated energy input and in the Jupiter model with the observed aurora, the magnitude, order of magnitude is actually the same. So which means the wave aurora is doing pretty good, but the kinetic physics is not good.
And so the Io flux tube has a parallel potential drop. And so there is, parallel acceleration and discrete, what we would call discrete aurora associated with that. And you see a bright spot at the foot plane of the Io flux tube. But again, that's very much a second order or, alien effect simulation.
Yeah, so what Mary talks about is this guy.
Yeah,
This is the
right there,
point
that
of
bright
the
spot.
Io. This is the Io moving through the Jovian magnetotail, launching these elfin waves.
Yeah.
And the tail is the reflection of the elfin waves between these two hemispheres.
Right.
So if you look at the infrared band, and these are like multiple spots.
Yeah, so
That's
we would
what
call
you were
that
talking
the
about.
discrete aurora.
Yeah.
Yeah.
Well, if you talk to Peter D'Armando, he'll tell you this is also a kinetic acceleration, bulk acceleration.
Okay, I have one last question.
Thank you so much.
Okay, well, one last question before we end, and you're free to go because we are over 1 hour. So when we do this planetary study, usually people think about the comparative magnetosphere, like want to get some implication for the Earth. So what's your comment on that? How would all these studies inform people working on the Earth?
It doesn't.
Some future time when the Earth spins up.
Okay.
This is a point, right? So there's something I didn't realize until my colleagues told me we taught this, right? Because you would think that we studied Earth for a long time, we know so much about the Earth, right? But right now, we don't even have observations like this of the Earth aurora. But at Jupiter, we have all these global observations from ultraviolet to X-ray to infrared, right? So it actually, to look at the detail of physics, regional physics, global, you have actually lots of data available, and more data available than the Earth. So he was asking me, like, why do you think that you have more data at Earth? Do you have a picture like this?
What we used to.
Imaging data.
Yeah, but nothing like that.
Well, it doesn't look like that. That's your point.
Now no matter where we are in the solar system. And well, thanks again for a great talk.